In the last lesson, we saw that heat naturally flows from a hot reservoir to a cold reservoir, and we stated this as one of the expressions of the second law of thermodynamics. Heat transfer occurs spontaneously from higher to lower temperature bodies, but never spontaneously in the reverse direction. If we place a heat engine between the hot and cold reservoir, the heat engine can process the energy from the hot reservoir and do some useful work with it. But only a fraction of the energy from the hot reservoir can be converted into work. There must be some heat left over to dump into the cold reservoir. And this is another expression of the second law of thermodynamics. So let me ask you two questions, and I really want you to think about the answer. Now, it doesn't matter if you get the answer wrong, but the act of actively engaging your mind to try and answer these two questions will help you make connections and gain a deeper insight into the material here. So the first question: in what situation in our daily lives would we want to move heat from a cold reservoir and expel it out into the hot reservoir? Now, as I've said before, this will never happen naturally or spontaneously, so we'd have to intervene and make it happen somehow. But why would we bother trying to do this in the first place? Well, this schematic here is essentially saying that we have a region or volume of space that is called the cold reservoir. Now, we'd want this space to be enclosed and thermally insulated. So this cold reservoir could be a room in a house, or in fact, the entire interior of a house, or it could be the enclosed space in a refrigerator. Where do you think the hot reservoir is in relation to these two examples? Well, for the house's interior, the hot reservoir would be the outside air of the house on a hot summer's day. The interior of the house will have the lower temperature compared to the outside air, and therefore the interior represents the cold reservoir. The same is true for the interior of the refrigerator. The inside air is the cold reservoir, and the air in the kitchen is the hot reservoir. So we can intuitively see now that if we do not have some sort of machine or process in place, heat will flow naturally from the kitchen, the hot reservoir, to the interior of the fridge, the cold reservoir. Or, for the example of the house, heat will transfer from the outside air on a hot summer's day to the house's interior until both the hot reservoir and the cold reservoir have reached thermal equilibrium. In other words, they reach the same temperature. So that's the answer to the first question. The second question is, how can we interrupt or reverse this flow of heat? In other words, how can we move heat from the cold reservoir to the hot reservoir and lower the temperature of our homes or refrigerator's interior? How can we make the cold reservoir even colder over time? Well, we need something called a heat pump. And when we supply work to this heat pump, it can transfer heat from a colder body to a hotter body. Now, I'll get into how this works in a minute, and I'll do this by explaining how a refrigerator operates. But it's important to realise here that the pump needs to be supplied with work for this transfer of heat to happen. It is impossible to transfer heat from a cold reservoir to a hot reservoir with a heat pump without doing work on the system. So the heat pump by itself cannot transfer heat from the cold reservoir to the hot reservoir. Work needs to be supplied to the heat pump. Now I'm going to show you exactly how a heat pump works within a refrigerator. And we're going to look at this cyclical process on a PV diagram, and we'll do this at the same time. So we saw in the last lesson that heat engines work in a cycle. For example, with a steam turbine, the internal energy of the water moving through the system will eventually return back to the same energy and therefore temperature as it returns back to the beginning of the cycle. Heat pumps also work in a cyclical manner, and this will become apparent in the next few minutes. So this is a simple diagram of our fridge. We have our cold reservoir here, and this is the region we'd like to cool. And you'll also see we've placed some thermal insulation around it to prevent heat from the outside getting in. Our hot reservoir is the surrounding space, in other words, everything outside our cold reservoir. This pipe here carries our refrigerant, and this is some substance that has a low boiling point. Now, while this refrigerant moves through this system, we can provide or transfer energy to it through work. In other words, through the compressor up here. Energy transfer can also be provided through heat. In other words, heat from the cold reservoir can be transferred to the refrigerant as it moves through the insulated fridge. But this refrigerant can also do work and expel heat through its cycle. And we'll get into the details of this in just a second. I'm also going to show you what happens to the pressure and the volume of the refrigerant as it moves through this cyclical process. And we'll do this on the PV diagram here. So at what point in the cycle should we start? So I'm going to start at state A, where we have an expansion valve. Now, it doesn't really matter where we start in this cyclical process, so long as we follow each state in its full cycle. So state A is where we have an expansion valve. Now, just before the valve, the refrigerant has a high pressure and temperature. And we can see this on our PV diagram. The refrigerant is also in a liquid state. Part A on our PV diagram sits on a higher temperature isotherm. When a high pressure liquid is forced through a small opening, it rapidly expands, and this is an adiabatic expansion. And this is because the expansion happens so fast that any surrounding heat doesn't have time to transfer into this liquid. As this refrigerant adiabatically expands into this pipe here, it does work on the surrounding refrigerant molecules. The high pressure refrigerant gives up some of its internal energy and transfers it to the molecules of refrigerant in the pipe after the valve. As we can see on our PV diagram, this adiabatic expansion leads us to state B. And you'll also notice the refrigerant is dropping to a lower isotherm. In other words, the temperature of this liquid has fallen during its adiabatic expansion. Now, why is this the case? So if we think about the first law of thermodynamics, could you explain to me why the refrigerant has dropped in temperature and therefore dropped in internal energy during this adiabatic expansion? Okay, so I've written out the first law here, which states that the change in internal energy of a closed system equals the amount of net heat transferred to this system minus the net work done by the system. We've already explained this expansion is adiabatic, which means it happens so rapidly that heat doesn't have time to transfer into the refrigerant, so Q must equal 0. We know that the high pressure refrigerant does work as it's pushed through the valve. So according to the first law, the change in internal energy is equal to negative work. The refrigerant gives up its internal energy through doing work, and therefore its temperature drops. Remember, the temperature of a substance is proportional to its internal energy, and we discussed this in a previous lesson. Okay, so we've got to state B, and the pipes with the refrigerant are now inside the cold reservoir. Now the refrigerant is still in a liquid state, but it also has a very low boiling point. So as it moves through the pipes in the fridge, it absorbs any heat from the cold reservoir and it starts to evaporate within the pipes. But during this phase change from liquid to gas, the refrigerant remains at a fixed temperature, even though it's absorbing heat. Now, why is this the case? So I explained this process in more detail in my video on phase change and latent heat, but have a look at the PV diagram here. When we move from state B to state C, this is an isothermal process. In other words, as the refrigerant is absorbing heat from the cold reservoir and its volume is increasing and its pressure is decreasing, its temperature remains fixed. Temperature always remains the same or constant during a phase change. So now the refrigerant is taking heat away from the cold reservoir and therefore cooling it down. At state C, the refrigerant vapour arrives at the heat pump. Now at this state, the refrigerant has a low temperature and pressure. The heat pump will now perform work on the gas and will put energy into this system. The piston here compresses the gas so fast that it doesn't have time to expel energy by heat into the surroundings. So this means this is an adiabatic compression, and therefore the change in internal energy of the refrigerant is equal to the work added to it. This increases the pressure and temperature of the gas, and we can see this on the PV diagram. We have jumped now to a higher temperature isotherm. So now the pipes and the refrigerant are outside in the hot reservoir, ready to expel heat to the outside world. But what was the point of the compressor here? Why couldn't we have just missed this step and sent the refrigerant straight into the hot reservoir? Well, just before the refrigerant reaches the compressor, it is still colder than the hot reservoir. A cold substance cannot spontaneously transfer its heat to a hotter substance. This would violate the second law of thermodynamics. The compressor's role is to increase the refrigerant's internal energy and therefore temperature through the transfer of work, so that the refrigerant can be heated above the temperature of the hot reservoir. As the refrigerant moves from D to A, it can now release this heat to the hot reservoir, and it does so isothermally. In other words, its temperature does not change during this process. And this is because the refrigerant is again changing phase, but now from a gas to a liquid, and it condenses as it gives up its heat. The cycle then repeats from A. So because we have to add work to the refrigerant, the amount of heat entering the kitchen or hot reservoir is always going to be greater than the amount of heat removed from the cold reservoir. This is why leaving the fridge door open will not cool down the kitchen. So if we go back to our schematic here, we can see that we need to add work to the refrigerant to ensure that heat can flow from the cold reservoir to the hot reservoir. Otherwise, the refrigerant will not be hot enough to expel heat into the hot reservoir. It needs to be hotter than the hot reservoir. Now, some heat pumps are more efficient than others, and more efficient heat pumps would use less work to remove the same amount of heat from the cold reservoir. But how can we measure this effectiveness? We can do this by measuring its coefficient of performance, or COP. And the COP is defined as the amount of heat pulled out of the cold reservoir divided by the amount of work it takes to do that. A good refrigerator should have a high COP of around 5 or 6. And a COP of 6 means that for every 100 joules of work being put into the system by the compressor, by the heat pump, will result in 600 joules of heat removed from the cold reservoir. Now there's one last thing before we finish this lesson. I want you to tell me in the comments below how we can use a heat pump to heat a home in winter. Now we explained how we can use a heat pump to cool down an interior space, but how can we use a heat pump to heat up an interior space where the outside air is a lot cooler? Where is the cold reservoir and the hot reservoir in this example? How would the refrigerant travel around this system, and where is the heat coming from to heat the interior of the home? Now, I don't want you to stress about providing the perfect answer here or even getting it entirely correct. This exercise is meant to help you get into the practice of questioning what you're being taught and really getting to the bottom of why things work. In the next few lessons, we'll look at the Carnot and gasoline engines. Then we'll cover the topic of entropy, which can be a rather tricky topic to get your head around.